Welcome back to Unwind. Learn while you fall asleep. There are no ads on this channel, ever. Just calm, uninterrupted learning while you rest. Tonight, we are covering cosmology, the Big Bang. If there is a topic you would like us to make next, leave it in the comments. We read them all, and we will create it for you. The room is very quiet now. You can feel the weight of the blanket resting across your shoulders, the way it settles into the curves of your body. The pillow has found its shape beneath your head. There is nothing left to do today. No problems waiting. No decisions calling for your attention. Just the dark and the stillness and the slow rhythm of your own breathing. And as that quiet deepens, let your mind begin to wander. Not far, just gently, towards something very large and very old, toward the beginning of everything, toward a moment that happened so long ago that time itself had not yet learned to measure its own passing. There was a man named Edwin Hubble who spent his evenings looking through a telescope on a mountain in California. This was in the 1920s, when the nights above Los Angeles were still dark enough to see clearly. The telescope was enormous, housed in a white dome that opened to the sky like a mechanical flower. Hubble was patient. He would sit for hours, his eye pressed to the lens, watching distant points of light. He was not looking for anything dramatic. He was simply measuring, recording, noting the small shifts in color that starlight carried across the vast emptiness of space. The mountain was called Mount Wilson. It rose above the city, above the haze and dust, into air that was clean and thin and steady. The telescope had been built there specifically for that steadiness, for the way the atmosphere above the mountain remained calm on clear nights. The dome itself was painted white to reflect the heat of the day. Inside, the telescope rose like a cathedral column, its metal surfaces cooled to the touch once the sun had set. The mechanism that turned it was precise, engineered to track the slow rotation of the Earth so that distant objects would remain centered in the field of view. Hubble would arrive in the evening, after the sun had set and the dome had cooled. He would climb the stairs to the observing platform, settle into the observer's chair, and begin the slow work of positioning the telescope. Each target had to be found carefully, adjusted precisely, tracked as the Earth turned beneath the stars. The chair was designed to move with the telescope, keeping the observer in position as the great instrument swung across the sky. It was a strange feeling, sitting there in the darkness, the only sound the quiet hum of the motors and the occasional creak of metal adjusting to the night's temperature. What he found was something very quiet and very strange. The galaxies were moving, all of them, not in random directions but outward, away from each other, away from some central point that no longer existed in space, but persisted in time. The light from distant galaxies was stretched, pulled toward the red end of the spectrum by their motion. The farther away a galaxy was, the faster it seemed to be receding. It was as if the universe itself was expanding, carrying everything with it like cities printed on the surface of an inflating balloon. Hubble published his observations in 1929. The paper was careful and measured. It did not claim to explain the universe. It simply presented the numbers, the measurements, the quiet certainty of what the light revealed. The paper was only a few pages long. It appeared in the proceedings of the National Academy of Sciences. Most people did not read it, even among astronomers. It took time for the implications to settle in, for the meaning to become clear. But the implication was unavoidable. If everything was moving apart now, then at some point in the past, everything must have been closer together. Much closer. Unimaginably closer. The idea sat uncomfortably in the scientific community for years. It seemed too simple, too strange. A universe that had a beginning felt more like theology than physics. Many scientists preferred the steady-state model, which suggested the universe had always existed, unchanging in its essential nature, with new matter constantly appearing to fill the gaps left by expansion. The steady-state model was elegant in its own way. It required no beginning, no moment of creation. The universe simply was, and had always been, and would always be. New hydrogen atoms appeared spontaneously in the empty spaces between galaxies, slowly enough that no one would ever notice, but fast enough to maintain a constant average density as the universe expanded. It was a comfortable idea. It fit with a certain philosophical preference for an eternal cosmos, unchanging in its fundamental nature, even as its details shifted and evolved. But the evidence continued to accumulate, slowly and patiently, the way water wears down stone. In the 1940s, a physicist named George Gamow began to think about what the early universe might have been like. Not philosophically, but mathematically. If you ran the expansion backward, compressing everything into a smaller and smaller space, the temperature would rise. The density would become extraordinary. Matter as we know it could not exist in such conditions. Gamow was a large man with a booming laugh and a talent for explaining complex ideas simply. He had come to America from Russia in the 1930s, part of a generation of physicists who had fled Europe as the political situation darkened. He worked at George Washington University, teaching and thinking about the fundamental nature of matter and energy. He would sit in his office, surrounded by books and papers, working through equations that described matter under extreme conditions. Conditions that had never been observed in any laboratory. Conditions that could only have existed in the earliest moments of the universe. He imagined a state of pure energy, unimaginably hot, where particles and radiation were indistinguishable from each other. He called it the primeval atom, though it was not really an atom at all. It was everything. All the matter and energy that would ever exist, compressed into a volume smaller than a single room. And then, for reasons that physics cannot fully explain, it began to expand. Not into empty space, because there was no space yet. Space itself was expanding, being created in the act of expansion. Time began its forward motion. The universe, in a sense that feels almost too large to hold comfortably in the mind, began. This moment, this beginning, came to be called the Big Bang, though the name is somewhat misleading. There was no explosion in the traditional sense, no shrapnel flying outward from a central point, just an expansion, smooth and uniform, happening everywhere at once. The name itself was coined by Fred Hoyle, a British astronomer who actually disagreed with the theory. He used the term dismissively during a radio broadcast in 1949, trying to make the idea sound absurd. But the name stuck, the way names often do, regardless of the intentions behind them. Hoyle was a proponent of the steady-state model. He was brilliant and stubborn, and he continued to defend his preferred theory long after most of his colleagues had accepted the evidence for the Big Bang. He made important contributions to our understanding of how elements are formed in stars, even as he resisted the idea that the universe itself had a beginning. In the first fraction of a second, The universe was far too hot for matter to form. There were only particles of pure energy, colliding and transforming in a dense plasma that filled all of existence. The temperature was trillions of degrees. The forces that govern the universe today, gravity, electromagnetism, the strong and weak nuclear forces, were unified into a single force that we still do not fully understand. This was the Planck epoch, named after the physicist Max Planck. It lasted approximately 10 to the negative 43 seconds, a decimal point followed by 42 zeros, and then a 1. A duration so brief that our ordinary sense of time cannot accommodate it. During this epoch, quantum effects dominated. Space and time themselves fluctuated wildly at the smallest scales. The smooth fabric of space-time that we experience today had not yet settled into its familiar form. Everything was uncertain, probabilistic, governed by laws that we are still working to understand. The physics of this era is still largely theoretical. We can write equations that describe it, but we cannot test them directly. The energies involved are far beyond anything we can create in particle accelerators. We are limited to mathematical models and indirect observations, piecing together the story from the evidence that remains. As the universe expanded, it cooled. This happened very quickly at first. Within the first second, the temperature had dropped enough for quarks to bind together into protons and neutrons. These are the building blocks of atomic nuclei, though they would not form complete atoms for quite some time. The early universe was still far too energetic for that. Quarks are fundamental particles, constituents of protons and neutrons. Under normal conditions, they are never found alone. They are always bound together in groups of 2 or 3 by the strong nuclear force, which is aptly named. It is the strongest of the 4 fundamental forces, powerful enough to overcome the electromagnetic repulsion between positively charged protons and hold atomic nuclei together. In the first microsecond after the Big Bang, the universe was hot enough that quarks could exist freely, unbound. This period is called the quark epoch, but as the temperature dropped below a certain threshold, the quarks began to confine themselves into protons and neutrons. The process was rapid and universal. Within a few microseconds, all the free quarks had been captured. The strong force operates only at very short ranges, about the diameter of an atomic nucleus. But within that range, it is immensely powerful. It has to be, to hold protons together despite their electromagnetic repulsion. 2 protons placed close together will naturally push apart because they both carry positive charge. The strong force binds them anyway. For the first 3 minutes, the universe was a kind of cosmic furnace, fusing protons and neutrons into the lightest elements. Hydrogen, which is simply a single proton. Helium, which is 2 protons and 2 neutrons bound together. Small amounts of lithium and beryllium. This process is called Big Bang nucleosynthesis. It happened in a very narrow window of time when the temperature was high enough for nuclear fusion to occur, but low enough for nuclei to remain stable once formed. The fusion reactions were the same ones that power stars today, but they happened under different conditions. The universe was filled with a hot, dense plasma of protons, neutrons, and electrons, all colliding constantly. Protons fused to form deuterium, a heavy form of hydrogen with 1 proton and 1 neutron. Deuterium nuclei fused to form helium-3 and helium-4. A few helium nuclei fused to form lithium-7. The reactions followed predictable paths governed by the laws of nuclear physics. Each type of nucleus has a specific binding energy, a measure of how tightly its protons and neutrons are held together. Helium-4 is particularly stable, which is why so much of it was produced in those first 3 minutes. And then the temperature dropped too low for fusion to continue. The cosmic furnace went quiet. The proportions of elements were set, locked in by the conditions of those first few minutes. Roughly 3/4 hydrogen, 1/4 helium, with just traces of anything heavier. Those proportions have remained remarkably constant throughout the history of the universe. Every measurement we make of distant gas clouds, of ancient stars, of the space between galaxies, confirms the predictions made by Big Bang theory. The universe remembers its beginning in the chemistry of its simplest atoms. This is one of the most compelling pieces of evidence for the Big Bang. The abundances of hydrogen and helium match the theoretical predictions with extraordinary precision. No other model of the universe's origin can explain why these proportions are what they are. The measurements have been refined over decades. Astronomers have observed the spectra of distant quasars, looking at the light that has passed through clouds of primordial gas. They have studied the oldest stars, which formed from material that was barely enriched by previous generations. The numbers always come out the same: 3/4 hydrogen, 1/4 helium, traces of lithium. But for a long time after those first minutes, the universe was still too hot for atoms to form properly. Electrons could not settle into stable orbits around nuclei. They were constantly being knocked free by the intense radiation that filled all of space. This meant the universe was opaque. Light could not travel freely. Photons would move a short distance, collide with a free electron, scatter in a new direction, collide again. It was like trying to see through a thick fog, except the fog was made of plasma and filled the entire cosmos. The universe during this time was a glowing soup of particles and radiation. Everything was in constant motion, constantly interacting. The photons and electrons were coupled together, unable to separate. The radiation pressure was so intense that it prevented matter from collapsing under its own gravity. No structures could form, no stars, no galaxies, no planets. Just a uniform, glowing haze. The temperature was still thousands of degrees, hot enough to keep electrons moving too quickly to be captured by atomic nuclei, hot enough to keep the universe bright and featureless. This period lasted for about 380,000 years, a long time by human standards, but brief in the life of a universe. And then, as the temperature continued to drop, something remarkable happened. The electrons finally slowed down enough to be captured by atomic nuclei. Hydrogen atoms formed. Helium atoms formed. The fog cleared. This moment is called recombination, though the name is slightly misleading. The electrons were not recombining with nuclei they had previously been bound to. They were combining for the first time, but the term has stuck, and astronomers still use it today. For the first time, light could travel freely across the universe. The photons that were released in that moment have been traveling ever since. As the universe expanded, their wavelength stretched, shifting from visible light to infrared to microwave radiation. Today, those photons fill the entire sky, arriving from every direction with almost perfect uniformity. We call this the cosmic microwave background. It is the oldest light in the universe, a kind of baby picture of the cosmos taken when it was just 380,000 years old. Astronomers detected it in 1964, quite by accident, when two engineers at Bell Labs were trying to eliminate a persistent hiss from a radio antenna. The two engineers were Arno Penzias and Robert Wilson. They were working with a large horn-shaped antenna in New Jersey, originally built for satellite communications. But no matter what they did, they could not get rid of a faint background noise. It was always there, coming from every direction, never changing. They cleaned the antenna. They checked all the electronics. They even removed a family of pigeons that had been nesting inside the horn, thinking perhaps the bird droppings were causing interference. Nothing worked. The hiss remained. The antenna stood in a field in Holmdel, New Jersey. It was a curious structure, shaped like a giant horn pointing at the sky. It had been built to receive signals from early communication satellites. But by the time Penzias and Wilson were using it, satellite technology had moved on. The antenna was available for other research. The hiss would not go away. It came from every direction. It was always there, day and night, summer and winter. Eventually, they realized they were not hearing noise. They were hearing the universe itself, still glowing faintly from the heat of its own beginning. Penzias and Wilson were awarded the Nobel Prize in Physics in 1978 for their discovery. It was one of the most important observational confirmations of Big Bang theory, proof that the universe had indeed been much hotter and denser in the past. The cosmic microwave background is almost perfectly uniform, which tells us the early universe was extraordinarily smooth. But there are tiny variations, small fluctuations in temperature that amount to only a few millionths of a degree. These fluctuations are important. They represent slight differences in density, tiny regions where matter was just slightly more concentrated than average. These fluctuations were first detected by a satellite called COBE, the Cosmic Background Explorer, launched in 1989. The satellite measured the temperature of the cosmic microwave background across the entire sky with unprecedented precision. The variations it found were incredibly small, but they were there, etched into the fabric of the universe like fingerprints from the moment of recombination. COBE orbited the Earth for 4 years, slowly scanning the sky, building up a complete map of the cosmic microwave background. The data it collected filled volumes. The analysis took years, but the result was worth the wait. The universe had structure, even in its infancy. Later satellites, with names like MAPI and Planck, measured these fluctuations in even greater detail. They created maps of the cosmic microwave background that show the temperature variations in exquisite detail. These maps are among the most important images in all of science. They show us what the universe looked like when it was young, before stars and galaxies had formed. The Planck satellite, launched in 2009, was the most precise of all. It measured the cosmic microwave background with such accuracy that it could detect temperature differences of a few millionths of a degree. The maps it produced are beautiful in their way, swirls of color representing tiny variations in the temperature of the early universe. Gravity, patient and persistent, began to pull on those denser regions. Over millions of years they grew. Matter accumulated. The first stars began to form, then the first galaxies, then clusters of galaxies, then vast filaments and walls of galaxies stretching across hundreds of millions of light years. The structure of the universe today, the great cosmic web of matter and void, grew from those tiny imperfections in the cosmic microwave background. The seeds were planted in the first moments after the Big Bang. The first stars formed roughly 100 to 200 million years after the Big Bang. This period is called the cosmic dawn. Before this time, the universe was dark. There were no sources of light except the fading glow of the cosmic microwave background, which had by then cooled into the infrared and was no longer visible to the eye. These first stars, were different from the stars we see today. They were made entirely of hydrogen and helium, with no heavier elements at all. They were massive, perhaps 100 times the mass of the sun, and they burned hot and bright and fast. Their lifetimes were measured in millions of years, not billions. When these first stars died, they exploded as supernovae, scattering the heavier elements they had forged in their cores: carbon, oxygen, nitrogen, iron. These elements mixed with the surrounding gas and were incorporated into the next generation of stars. Each generation enriched the universe a little more, building up the periodic table, element by element. The process was gradual, but inevitable. Each star that lived and died left behind a chemical legacy. The interstellar medium, the gas between the stars, slowly became enriched with heavy elements. By the time the sun formed, about 4.6 billion years ago, the gas from which it condensed contained about 2% heavy elements. That was enough to allow rocky planets to form. But there was something strange about the way galaxies moved. When astronomers measured the rotation of spiral galaxies in the 1970s, they found that stars far from the galactic center were moving faster than they should. According to the visible matter alone, those outer stars should have been flung off into space long ago. Something unseen was holding them in place. Something with mass, with gravity, but no light. The astronomer who first noticed this was Vera Rubin. She spent years measuring the rotation curves of galaxies, carefully plotting the velocities of stars at different distances from the galactic center. The pattern she found was consistent across dozens of galaxies. The stars in the outer regions were moving too fast. The visible matter could not account for their motion. Rubin worked at the Carnegie Institution in Washington, D.C. She often observed at Kitt Peak National Observatory in Arizona, spending long nights at the telescope, measuring the spectra of galaxies. The work was meticulous and time-consuming. Each galaxy required hours of observation. Each spectrum had to be carefully analyzed to extract the velocity information. They called it dark matter, though the name is more a confession of ignorance than a description. It does not emit light. It does not absorb light. It does not interact with electromagnetic radiation at all, as far as we can tell. It makes itself known only through gravity, through the way it bends space and holds galaxies together. We now believe that dark matter makes up about 85% of all matter in the universe. Everything we can see, stars, planets, gas clouds, galaxies, is only a small fraction of what exists. The rest is invisible, detectable only by its gravitational influence on the things we can observe. Dark matter forms vast halos around galaxies, extending far beyond the visible stars. These halos provide the gravitational scaffolding that allows galaxies to form and remain stable. Without dark matter, galaxies as we know them could not exist. The visible matter would not have enough gravity to hold itself together. Computer simulations of galaxy formation show this clearly. When astronomers model the formation of galaxies using only visible matter, the results do not match what we observe. The galaxies that form in these simulations are too small, too fragile. They fall apart easily. But when dark matter is included in the simulations, galaxies form that look like the ones we see in the real universe. This was humbling for physics. The universe turned out to be far stranger, far less visible than anyone had imagined. And there was more strangeness to come. In the 1990s, astronomers were measuring distant supernovae. trying to determine how much the expansion of the universe had slowed down over time. Gravity, after all, should be pulling everything back together, gradually decelerating the expansion that began with the Big Bang. The supernovae they were studying were a special type called Type Ia. These supernovae are remarkably consistent in their brightness, which makes them useful as standard candles. By measuring how bright they appear from Earth, astronomers can calculate how far away they are. And by measuring the redshift of their light, astronomers can determine how fast they are moving away from us. Type Ia supernovae occur in binary star systems, where one star is a white dwarf. The white dwarf pulls matter from its companion star. When the white dwarf reaches a critical mass, about 1.4 times, the collapse triggers a thermonuclear explosion that destroys the entire star. Because the explosion always happens at the same mass, Type Ia supernovae always have approximately the same intrinsic brightness. This makes them extremely useful for measuring cosmic distances. 2 independent teams were conducting this research. One was led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees. Both teams were meticulous, measuring dozens of supernovae, checking and rechecking their data. But the measurements showed something unexpected. The expansion was not slowing down, it was speeding up. The result was so strange that both teams initially thought they had made a mistake. They checked their instruments, their calculations, their assumptions. But the data held. The distant supernovae were fainter than they should be, which meant they were farther away than expected, which meant the universe had expanded faster than predicted. Something was pushing the universe apart, acting against gravity, causing galaxies to accelerate away from each other. This mysterious influence came to be called dark energy, and it appears to make up about 68% of the total energy content of the universe. We do not know what it is. We do not know why it exists. We can measure its effects, but we cannot explain its nature. It is simply there, woven into the fabric of space itself, driving the universe toward an ever faster expansion. Some physicists think dark energy might be related to the cosmological constant, a term that Einstein introduced into his equations of general relativity. Einstein later called it his greatest blunder, but it turns out the universe may have needed it after all. The cosmological constant represents a kind of energy inherent in empty space itself, a constant pressure that pushes outward against gravity. Einstein introduced the cosmological constant in 1917 because he wanted his equations to describe a static universe, neither expanding nor contracting. At the time, no one knew the universe was expanding. When Hubble's observations showed that it was, Einstein abandoned the cosmological constant. But now it seems the universe may need something like it after all. So the universe we inhabit is made mostly of things we cannot see and do not understand. Ordinary matter, the stuff of stars and planets and people, makes up less than 5% of the total. The rest is dark matter and dark energy, invisible and mysterious, known to us only by their gravitational signatures and their influence on the cosmos at large. This is not a failure of science. It is simply where we are in the long process of understanding. The questions are clear. The measurements are precise. The answers will come. In time, the way answers always do. Slowly, through careful observation and patient thought. There is one more piece to the story of the early universe. One more refinement to the picture of the Big Bang. It concerns the very first moment, the tiniest fraction of a second after the beginning. In the 1980s, a physicist named Alan Guth proposed that the universe underwent a period of extraordinarily rapid expansion in its first instance. This period, called cosmic inflation, lasted less than a trillionth of a second, but in that time, the universe expanded by a factor of at least 10 to the 26th power. It sounds absurd, almost impossible. But inflation solves several problems that had puzzled cosmologists for years. It explains why the universe is so uniform, why the cosmic microwave background looks almost the same in every direction. Inflation stretched the universe so quickly that regions which had been in contact, which had reached the same temperature, were suddenly separated by vast distances. Before inflation was proposed, cosmologists faced what was called the horizon problem. Different regions of the universe, separated by vast distances, had the same temperature to an extraordinary degree of precision. But according to the standard Big Bang model, these regions had never been in contact with each other. Light had not had time to travel between them. So how did they reach the same temperature? Inflation provided an answer. Before inflation, the entire observable universe was compressed into a region, small enough that all parts of it were in thermal contact. Everything reached the same temperature. Then inflation stretched this small uniform region to an enormous size. The uniformity we see today is a relic of that early contact. It also explains the tiny fluctuations in the cosmic microwave background. Quantum fluctuations, normally confined to subatomic scales, were stretched by inflation to cosmic proportions. Those fluctuations became the seeds of galaxies, the small imperfections that gravity could work with over billions of years. Inflation remains a theory, not yet confirmed by direct observation, but it fits the data we have remarkably well. It makes predictions that match what we see when we look at the oldest light in the universe. One prediction of inflation is that it should have produced gravitational waves, ripples in the fabric of space-time itself. These primordial gravitational waves would have left a subtle imprint on the cosmic microwave background, a particular pattern in the polarization of the light. Astronomers are searching for this signature now, using telescopes at the South Pole and in the deserts of Chile. The telescopes are located in some of the most remote places on Earth, chosen for their dry, stable atmospheres. The South Pole telescope sits on a plateau of ice 2 miles thick. The Atacama Desert in Chile is one of the driest places on the planet. In both locations, the air is thin and clear, ideal for observing the faint signals from the early universe. The story of the Big Bang is not complete. There are questions we cannot yet answer. What came before the Big Bang? If the question even makes sense. What caused inflation to begin? And why did it stop? What is the true nature of dark matter and dark energy? These questions remain open. The universe is still teaching us, still revealing itself slowly through the light it sends across billions of years of space and time. But what we do know is extraordinary enough. We know the universe had a beginning. We know it has been expanding and cooling for 13.8 billion years. We know the light we see from distant galaxies left those galaxies when the universe was younger, smaller, hotter. We are looking back in time whenever we look up at the night sky. The most distant galaxies we can see are more than 13 billion light-years away. The light we receive from them today left those galaxies when the universe was less than 1 billion years old. We are seeing them as they were in their infancy, when they were just beginning to form stars, when the first heavy elements were just beginning to appear. There are galaxies so far away that their light has not yet reached us. There are regions of the universe we will never see, not because they do not exist, but because the light from them will never have time to cross the expanding space between us. The universe is larger than the observable universe. How much larger, we do not know. The observable universe has a radius of about 46 billion light-years. This is larger than 13.8 billion light-years, because space itself has been expanding while the light has been traveling. A photon that left a distant galaxy 13 billion years ago has been traveling through expanding space all that time. The galaxy it left from is now much farther away than it was when the photon began its journey. The atoms in your body were not made in the Big Bang. They are too heavy for that. They were forged in the cores of stars that lived and died long before the sun was born. Those stars fused hydrogen into helium, helium into carbon and oxygen, built up the periodic table element by element through millions of years of nuclear fusion. The carbon in your cells, the oxygen you breathe, the calcium in your bones, the iron in your blood. All of it was made inside stars. The stars were vast nuclear furnaces, converting lighter elements into heavier ones, releasing energy in the process. This is what makes stars shine. The light of the sun is the light of nuclear fusion, of hydrogen becoming helium deep in the solar core. And when those stars exhausted their fuel, they collapsed and exploded, scattering their enriched material into space. That material drifted through the galaxy, mixed with gas and dust, and eventually collected into a new generation of stars. One of those stars was the sun. One of the planets that formed around it was Earth. The sun formed about 4.6 billion years ago, in a cloud of gas and dust left over from previous generations of stars. The cloud collapsed under its own gravity, spinning faster as it contracted, flattening into a disk. Most of the material fell into the center and became the sun. The rest remained in orbit, gradually clumping together to form planets, moons, asteroids, and comets. The early solar system was a chaotic place. Planetesimals, small rocky bodies, collided and merged. Some grew large enough to become planets. Others remained small, becoming the asteroids and comets we see today. The Earth was struck repeatedly by large impacts, including one collision with a Mars-sized object that created the Moon. That collision happened about 4.5 billion years ago, not long after the Earth had formed. The impact was so violent that it melted both bodies, mixing their material together. Some of the debris was thrown into orbit around the Earth, where it gradually coalesced to form the Moon. The rest fell back to Earth, or escaped into space. And here you are, made of stardust, lying quietly in the dark, thinking about the universe that made you. The room is very still now. The blanket has grown warmer. Your breathing has slowed. The day is far behind you, and tomorrow is not yet here. There is only this moment, this quiet, this gentle dark. The air in the room has settled. The temperature is steady. Outside, the world continues, but it is distant now, separate. It does not require your attention. Your body has found its position of rest. The muscles have released their tension. The mind has stopped its planning, its worrying, its endless cataloguing of tasks and concerns. And somewhere, very far away, galaxies are still moving apart. Stars are still burning. Light is still traveling across the vast empty spaces, carrying information about things that happened billions of years ago. The Andromeda Galaxy, our nearest large neighbor, is moving toward us at about 110 kilometers per second. In about 4 billion years, it will collide with the Milky Way. The two galaxies will merge, They're stars passing by each other like ghosts, almost never colliding because the distances between stars are so vast. The merged galaxy will be larger, older, quieter. But all of that is very distant now, very far away. The universe is large and old and patient, and you are here, safe and warm, drifting slowly towards sleep. The pillow beneath your head holds you gently. The sheets have warmed to the temperature of your skin. Everything is soft now. Everything is calm. The story is ending, the way all stories do. Not with answers to every question, just with the quiet that comes when the telling is done. The cosmic microwave background is still there, filling the sky with its faint glow. The galaxies are still spinning. The stars are still fusing hydrogen into helium, creating light and heat and the elements that make life possible. But these things are happening without you now. They will continue while you sleep. The universe does not require witnesses. It simply is. The stars are still there, beyond the ceiling, beyond the sky. They will be there tomorrow. For now, there is only rest, only the slow dissolving of thought into dream. The edges of consciousness are softening. The boundary between waking and sleeping is blurring. Soon there will be no thoughts at all, just the deep rest that the body needs, the restoration that comes with sleep. Your breath has found its rhythm, in and out, slow and steady. The body knows what to do. It has done this every night of your life. It knows how to let go. Only the darkness, soft and complete. The room around you is holding you gently. The bed beneath you is solid and supportive. The pillow cradles your head. The blanket keeps you warm. Everything is as it should be. Everything is quiet. Everything is still. The universe continues its slow expansion. Dark energy pushes galaxies apart. Dark matter holds them together. Ordinary matter forms stars and planets and people. But these are just words now, just sounds. They have no weight, no urgency. They fade into the background, into the quiet hum of existence, and sleep.